I am pleased to introduce Kent Nebergall, Starlink's Children, Opportunities for Massive Satellite Constellations.
Okay, back up. So this was the Elon Musk tweet that started this whole thing. Basically, Elon said, we should send probes to the outer solar system and get high-res, true-color images of strange things out there. Maybe there's an alien artifact. And everyday astronaut, of course, chimed in and said, what are you going to do about launching, a large payload on that trajectory? And where this gets interesting is that Elon then turns around and says something about, massive delta velocity slam with high, blah, 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 can be lightened with Starship with no heat shield and fins or legs. So basically he's saying, let's make a disposable version of Starship. And that seems like an abomination considering how long we've waited for something like this to happen. I mean, literally 100 years when it gets down to it. So the idea of throwing one of these away just seems like, a horrible thing. But when you think about it, if they did an extendable version, you don't need a heat shield, you don't need legs, canards, you'll need RCS. You may or may not need solar panels, depending on how far you go with this thing and the payload together. But if you carry your solar panels with you, you can extend the glide, so to speak, on it. Refueling, you definitely have to refuel it in orbit to get the maximum payload out. So what kind of probes is he talking about? Well, if he does something based on Starlink, which, he's already talking about cranking out thousands of these things, then that seems like a good foundation, and that's what we're going to get into. When it comes to these low latency systems for Earth, we have three major areas: communication, observation, and intelligence. And this is where a lot of the new satellite technologies are going. So Starlink itself, 12,000 satellites. Just for reference, the total number of satellites that are currently in orbit, 5,000. Number that are operational, slightly under 2,000. So 6 times the total number of operational satellites. And oh, by the way, if you've seen the news in the last couple of days, he's talking about putting in another 30,000 or 36,000. I forgot exactly. I was just reading it before I got here. But they're only 227 kilograms each. On the test fleet, they'd be a little heavier for the live one because this doesn't have the laser communication backbone that goes along and bounces the signal from satellite to satellite. 2024 completion date for half of it, 2027 for all of it. Estimated cost $10 billion. This stat really blows me away. This idea of 50% of the backhaul traffic of the internet on this system. Because if you're going from satellite to satellite to satellite via laser in a vacuum, it's faster than going through a fiber optic through the ocean and going from repeater to repeater to repeater, because light just travels faster in a vacuum than it does in glass. So do they have competition? Well, sort of. There's a few other systems that are talking about doing stuff along these lines, but Amazon is, of course, anything Elon does, Jeff talks about doing as well. So Project Kuiper is a 3,000 satellite constellation, but we haven't seen much about it. Now, if we want to get into optical stuff, it was kind of neat watching the presentation on small sats this morning because they talked about Planet Labs. Planet Labs' own satellite constellation are these little 3U telescopes that look down at the Earth. Well, 3U CubeSats. They're literally this big, little tiny telescopes, but they can still get 50-meter resolution off these things. And there's several other systems. You'll notice there's kind of a trend here. 2 of these systems have been bought out by Planet Labs, and you'll see why on the next slide. The mid-range systems are things like what France and Germany and places like this have done. They're basically the spot satellites, which were commercial, but they were high. They weren't as good as a spy satellite, but they were a lot better than anything that existed at the time. And those constellations go back a couple of decades. And then just for reference, in our National Reconnaissance Office, Keyhole satellite is basically a Hubble looking straight down, so it's billions of dollars. And it's quite a, but we're talking about 7-centimeter resolution on the one hand. So, and that's limited by the optics. So we've been having that resolution since the early 70s. or late 70s at least, because they were able to, it's limited by how fine you can make the mirrors and so forth, bigger mirror, higher resolution, better brightness, all that fun stuff. So the problem with these systems is they are completely not in the same universe as each other, partly because of the optics, partly because of the price, partly because of the size. But you'll notice the orders of magnitude difference when I tried to divide. I tried to make a metric that would match all of them, and it just kept failing. I got 0.0013 on one number, and I've got 1,587 on the keyhole. So they fell into certain groups, and what I noticed is that the new space stuff, the two systems that were out of, one was out of, I think, Germany, and all that, they were building relatively small systems. Planet Labs ended up buying those companies. So when you go to their website to see what their capability is, it's a little muddy because they're talking about their little 3U satellites, but they're also talking about these other ones that are about the size of a mini fridge that are more capable and weigh about 100 kilograms. So there we go. So in addition to that, as again, they were talking about this morning, there are CubeSat-sized and backpack-sized radar systems that are being used for Earth observation, and there are proposals for using them for deep space work. Now, you'll notice in this picture, that's a fairly small satellite. It's about, 4U across, but it's got a relatively large radar array because the longer the antenna, the lower the frequency, the better the penetration into the ground. So you've got that's a little different than the way Starlink does things, because Starlink has a phase array about the size of this table or so. And then there's deep space things where we're talking about doing these at the moon and Jupiter. Military implications of all this. The Cold War had a certain balance to it for 2 or 3 generations. We had these big, massive spy satellites that were able to keep an eye on things, make sure that nobody was going to invade anybody anytime soon. But that also meant that if you wanted to invade somebody, you weren't going to do it anytime soon without being detected. Aircraft carriers were basically like a small city, military base anywhere that could be put in the world by the United States and nobody else. And then we had the distant early warning line, which were these massive radars stretching from Alaska all the way to Greenland that looked over the North Pole to see if any Russian missiles were coming the other way. And they would look as far over the horizon as possible to give as much warning as possible. There were smaller radars around the coast because we had to also look for systems coming off of submarines. But they weren't completely unprotected, but they were not at the level of that. So what Russia and China have talked about doing is making hypersonic missiles that could take out the aircraft carriers and overwhelm the defenses. Well, the only solution to that is that you need a satellite-based radar that can look over the horizon as far as possible to see them coming and give you as much warning as possible. That same sort of system where you can look down and keep an eye on anything happening below you would also work if you were doing what Russia has proposed doing. They actually developed this in the early 70s, but they started talking about it recently under Putin, is the idea if you launch a missile on an orbital class vehicle, the opposite direction, fly it over Antarctica and come and blindside Florida from the opposite direction. So that has been around a while, but it's recently taken precedence because they're talking about doing these second strike weapons in some degree. And then these big heavy satellites, that of course made them vulnerable to ASAT systems where you take out one satellite, that's $1 billion asset that's not going to be replaced anytime soon. It's going to take maybe 5-10 years under current military contracting to replace it. Well, we've noticed that we can build these small satellites they're not as good, but we don't need to read newsprint. We just need to be able to see if there's a big troop movement. And these are plenty good for that. You can see some of these washing machine sized ones can see every car traveling in a city from above. So we can just as easily look for a tank concentration or so forth. So the good news is that we kind of get away from some of these risks of, if we have systems that blanket the world where we know every vehicle that's moving, The good news is that you have that same deterrence to war. You don't want to mass troops on a border and think that, oh, I'll just take out the satellites and they go overhead so nobody will know, and then I can launch my sneak attack. You don't have the possibility of somebody trying to overwhelm your carrier fleet or whatever. But the flip side of that, though, is that this is a lot of information coming in, and the way we tend to think of big data nowadays is, oh, we'll take artificial intelligence and we'll apply it to the problem. Well, what happens if you have an unscrupulous leader in some country who says, tell me when I've got the right conditions where I could launch a first strike? And the AI, which are not as smart as people think they are, you know, you've seen these things where they'll have a thing where it's like, we've got pictures of dogs over here and pictures of wolves over here, and then we show a picture of a dog and we think, oh, it's trained that it'll know it's a dog. And then one time it misidentifies a dog as a wolf. And then they say, okay, Mr. Artificial Intelligence, tell me what part of the picture you were looking at to tell me that that was a wolf versus a dog. And it shows you the snow in the background because all the pictures of the wolves were on a snowy day, and all the pictures of the dogs were on a sunny day, on the grass. And it had absolutely nothing to do with the dog or the wolf. These things happen, and these things have happened for quite a while in the idea of missile targeting systems and stuff like that. So the real problem is that we have a lot of natural stupidity to go with our artificial intelligence, and if we lean too heavily on systems like this, we can get in a very bad situation. So on to something more optimistic, exploring the solar system. Here's something most people have not heard of. There's an idea that if you take a laser and you pulse it into one of these skylight caves, like on the moon or Mars, where there's like a crater above a lava tube, you can actually bounce the laser a couple of times and look for this like echoed reflection as the signal comes through, and see a little bit further. It's a blurry image, but you can actually see a little bit into the cave, so to speak. So you get an idea of, okay, this one's real short, so it's not very good for settlement, but this one's huge. Hey, let's go land there and build our base. Well, if you're Starlink, you have these lasers that send very short pulses and they can listen for very short pulses because they're sending 50% of the internet backbone across these back of these satellites if they like. You've got the telescopes that can see those signals. You've got ion drive systems to maintain their position, but they can also be directed around. And you've got very light satellites. You've got AI for collision avoidance. And you've got this phase array communications antenna for, you know, talking to people on the ground and whatever. That's not good for doing mineralogical work where you're looking like feet underground. But if you're looking for missiles, aircraft, trying to make sure that somebody hasn't hijacked an airliner, it's the right size. It's a phase array exactly like in the nose of a fighter jet as far as the size goes. So just some variations if we kind of want to make a gift catalog essentially for SpaceX in terms of what they could build. Basic Starlink, if we go up to that, if we add that very small camera that's 50-meter resolution, we only go up 25 kilograms. If we take the big one that's the size of a washing machine, we get up to 5-meter resolution, but we only go up 100 kilograms. And then if we add one of these radar systems, like a mid-range one, well, we've got night images of Earth. We can do all kinds of stuff with that sort of thing. So if we were building a constellation around the moon or Mars or Venus or anywhere like that, this is just, if we had 100 satellites, what would we have those 100 satellites do? So, and this is assuming you've got settlements on Mars and so forth. Well, anywhere you go on Mars, you could be using these things like a spotlight to go look at that area with every hour. Like your base, you want to look at it every hour. If there's a place where you want to send an expedition, you could be watching it very routinely on these systems at resolutions that would be able to see a car. You can use radar, you can predict the weather more accurately. And then what you also have is global communication, which would then backbone to a higher constellation of satellites that would then beam as much of that data as possible back to Earth. And this would be, then you'd have another constellation around Earth that would pick up these, you know, you'd have one set of maybe a dozen satellites that all look straight at Mars all the time, when possible. Another set looking at any other world that had a constellation like this, or in deep space when we get to that on the asteroids. So you end up with a very your interplanetary internet built like that, so you can communicate in as close to real time as possible across the solar system. And if Earth and Mars are in transit with one another where the sun's in the way, you could theoretically bounce it to another constellation around another planet and then echo it back over to Earth with one constellation looking one way, one looking the other way. So if we send a fleet of these out to the asteroid field or all the way out to the Trojan asteroids that co-orbit with Jupiter, we have this sort of thing where we would have a fleet of satellites facing backwards and communicating in real time, or as close to real time as you can, and then another fleet that would be doing local communications. They could do radar penetration of an asteroid surface. They could bounce a signal from one off the edge of an asteroid and then bounce it out to get an incident thing, or they could try to bounce one with a lower frequency through the outside layers of the asteroid to another satellite on the opposite side. So you could X-ray these satellites and so forth. And if you're doing surveys looking for metals and stuff like that, as I was flying here from Chicago, I took a picture out the window, and I wish I'd managed to get it into the presentation, but you could see every little tiny lake in this section of the mountains, from down to like the size of this table, because the sunlight was hitting it from exactly the opposite angle, so it all just glowed white on the photo. So if you had that same sort of arrangement where you could see the reflections of any metals or anything valuable on the surface or mineral concentrations, and then you can tune the radar frequency to work around that. And then there's this idea that's been around for a little while. Focal is the idea of if you want to examine a star or the center of the galaxy or anything else that's of serious interest, you can actually send a group of telescopes in the opposite direction and use the sun as a lens, the gravity of the sun. But you have to go out 550 astronomical units, which is way further than we've ever been. I think we're up 50 now with Voyager. And it has to be a telescope that looks back. Well, that's exactly what we're talking about here. Now, the difference between this and what we've been talking about so far is kind of like the old joke about this axe belonged to George Washington. I had to replace the head twice and the handle 3 times. It's going to bear no resemblance to any of these systems. It's going to have to be nuclear powered. It's going to have a lot of variations, but it will be derived from the same family tree as what we've been talking about so far. And just a slight update on something I talked about last year I had talked about interstellar panspermia, and I said that the Gaia telescope was going to theoretically find other suns that were similar to ours from the same nebula from which our sun was born. And it has actually found one about 160 light years away that's almost identical to our sun. So that seems like a really good target for something like this. So what about having a business model for the here and now and not focusing on exploration or whatever? Well, you have Planet Labs has a viable business model. What happens if you tie that in with high-speed communication so that you don't have any kind of bottlenecks coming from a little telescope that has to communicate all this data to the ground? Now you're already attached to a high-speed communications backbone, so you can do as real time as you like. If any of these military threats become realized, of course, they could always launch a military version of the Starlink constellation to do radar, do another one for optical, and get past all the threats of unexpected attack or ASAT. Risk reduction for exploration. If you're going to Mars, you kind of want to know what the weather is like when you get there and not have any communication issues. And then, of course, asteroid mining, we can reconnaissance that quite a bit. So, any questions? Microphone, please.
So, the primary advantages of Starlink are basically that it's made by SpaceX, so SpaceX can launch it, and it's extremely cheap. They've just essentially totally ignored TRL levels in the normal paradigm. Mm-hmm. They're disposable, essentially, flown at low altitude. So if something goes wrong, they just deorbit on their own. So everything that you said for low Earth orbit and all the imaging of Earth, that makes sense. But why use Starlink as a model or a backbone for anything interplanetary? I mean, you're talking about much greater delta Vs. I mean, the delta V requirements at 550 kilometers are like a couple hundred meters per second. We're talking about, 3 kilometers per second or something like that. You've got much lower solar irradiance further away from the Earth. It's going to be hard to use solar power. So why use Starlink as sort of your starting point?
Mainly because this is Elon Musk has talked about putting these same satellites in orbit around Mars for communication there, so we have to address that. Now, getting back to your point, it's a lot harder to communicate between millions of people as opposed to thousands of people. So if they want to, they're going to have a lot lower bandwidth requirements there. The solar arrays on just that demo constellation, if you took all the solar arrays and stuck them together, was half as much as the entire International Space Station. Part of the reason I said that maybe you want to keep the solar arrays attached to the Starship launching it, the disposable one, is if you're going out to Mars, you're probably going to want to keep all those satellites on board and use the aero shell of it for aerobraking. So you still would need a heat shield and so forth, but it would be basically a cargo version of Starship with a much smaller payload of satellites, bigger fuel tanks because you're staying on station, a little better radiation hardening and so forth because you're not under the radiation belts and you don't have the Earth blocking it from the other direction. So they're tuned, they're not out-of-the-box Starlink systems, but the parts are there, the technology's there. It's just basically, it'd probably be second or third generation versions of Starlink parts. And, SpaceX is relentlessly tinkering with these systems, so it would probably be their fifth or sixth or seventh generation systems by then.
Thank you.
Hi there, Kent. Wonderful talk. If you look at having all of these satellites out there, what about the possibility of using them in coherent arrays, like is used with, for instance, the very large array of radio telescopes on Earth, where you take a number of smaller satellites and optically combine their information together? You can get much higher resolution.
Yeah, I'm really glad you brought that up because there are 2 points I missed and a third one, so I've got just a tiny little bit of time. One is a concept, I think, out of France called hypertelescope, and that's the idea of you have a bunch of little telescopes. Well, those are just basically mirrors that are all on a combiner. So something like this, yeah, theoretically you could do it if you can handle the tolerances of getting them in exactly the right place. Best way to do that is ion drive. Oh wait, we already have ion drive, so we're set there. Radar, that's actually a slide that I did not use. See this, this is a German experiment where they took radar signal off one, bounced it off the Earth, and picked it up on a second satellite. So if you had something like that where you're using the satellite constellation as something like a radar arrangement, then that's a possibility. And then the third thing, which I didn't know about until this morning, was the idea that if we had in the Lagrange points basically a big repository of all the biological stuff out there, and I was like, well, that's going to be anything from dust to rocks to whatever, all gathered in a space. What would be the perfect system for doing reconnaissance that? Well, it's going to be something that has a good optical telescope for finding those rocks, a good radar system for finding the dark ones, that can travel as a fleet. You see where this is going. So I think that's also a very high possibility.
But the other part is having a hyperspectral where you use one X-ray, one UV, one visible, one IR, one radar.
Yeah, that's the idea. Is you'd break it down. That's actually, I didn't explain it very clearly, but that's when I say radar multispectral.
Yeah.
This asteroid. That's exactly what I'm talking about.
Thank you.
Okay. Any others? We got 1 minute left. Oh, sure. Does this have anything to do with 5G? No, but I think 5G is pure 5G is kind of a joke because that signal is so high frequency, it doesn't go through skin, it doesn't go through air, very far anyway. So you have to have, your cell tower practically in the same room as you for it to work. And good luck getting a signal past your own hand when you're holding a receiver. So I think what Elon Musk could do as another business model is have something that's like a cell phone tower, but it's receiving from above, and then it broadcasts out conventional 4G within a relatively small cell. And especially in the third world, that would be absolutely perfect. Because you could extend anything anywhere from there. They're already kind of doing that, but you still have to have a backbone. Well, this is cheaper. All right, we're good.
Thank you.